Alright, we're going to solve some weak acid and weak base problems. This problem is a straightforward weak acid problem. What do you think is the first thing we always do for these types of problems? Go ahead and hit pause and start solving. Good, so the first thing we want to do is write out the reaction. So that's shown here. The acid dissociates into H plus ions and the anion, in this case acetate. And we just fill out our normal ICE table, set up the equilibrium concentrations, and solve for X by setting products over reactants equal to the K value that's been given. Alright, to find the actual pH, once you solve for X, that's the hydrogen ion concentration, also the hydronium ion concentration, so solve by taking the negative log of that. Excellent. Okay, to find the percent dissociation of pH, we essentially go through the exact same process. Go ahead and hit the pause button and try to solve each of these problems. And if you were stuck, here's some hints. These are two separate problems. First, you're solving for this 0.025 molar solution and the 0.0025 molar solution. First, for each one, write out the dissociation and set up an ICE table and solve for X. Then you'll note, to find the percent dissociation, that is literally just X divided by the initial concentration times 100. Alright, now that you've tried that one, here are a few more to try, so hit pause on this recording and try to solve for these before you move on. If you're stuck here, go to let the next slide go. See the hint, write the equation for the dissociation of the acid and use an ICE table. So you'll do that for the 2 molar solution as well as the 0.2 molar solution. Once you've done that, this is what the ICE table will look like. Now, of course, solve for X, which will give you the hydrogen ion concentration. And again, the percent ionization is just equal to X over the initial concentration times 100%. That's the percent that gets ionized or broken up. To solve for the pH, again, just the negative log of the hydrogen ion concentration, which from the ICE table is X. Moving on, here's another type of problem. Look at this formula right here. We need to determine, first of all, if this is an acid or a base. How do we know? Alright, well, if we look at the formula, notice it has the nitrogen in it. Nitrogen will always have a lone pair of electrons right there. This is actually a base. Notice it does not have a hydrogen in front, which would indicate an acid. And the fact that it has this nitrogen indicates that it's a base. Alright, so we want to calculate the pH of a 5 molar solution of methylamine. This is a methyl group and an amine. How do we start the problem? Hit pause and see if you can figure this out. If you decided to write out the reaction with water and then use an ICE table, that's excellent. Let's do that. So be careful when writing for a weak base the reaction with water. You always need to include the water molecule because the nitrogen will take off one of the hydrogens from the water molecule, making the positive ion as a product, leaving behind the hydroxide, which is what makes this really a base. So then you set up the ICE table as per normal. You start out with 5 molar of your base, set up the normal ICE table, and of course solve for X. Go ahead and hit pause, solve for X, and see if you can find the pH of this solution. Once you solve for X, X is equal to the hydroxide ion concentration. Make sure you see that in the ICE table. So then you find the pOH by taking the negative log of that number and subtracting from 14 to find the actual pH. All right, make sure that you can do that problem. You can try it again here. Hit pause if you need to. Now that you've seen how to do that problem, go ahead and try this one. Notice again, this is a base, this is ammonia, and it has that nitrogen with a lone pair of electrons, which will take hydrogen from the water molecule. So of course the first things to do would be write out the reaction in water and set up the ice table. Okay, go ahead and hit pause and solve this problem. All right, welcome back. Let's now take a look at Hess's law of acid and base reactions. So here we're going to write the equation for HA in water. HA is any old acid, a hydrogen ion attached to the anion. So you need to write the equation for that in water. And then take the anion from that reaction, use that as a base, and write the reaction for that base in water. Here are the two reactions. The acid will give up its H+, that's the definition of an acid, to make H3O+, and the anion. This anion, this is the conjugate base from that acid. We can now look at what that base does in water. It will take a hydrogen from the water molecule. Again, the definition of a base, it's a proton or hydrogen ion acceptor. Okay, when that happens, we leave behind the hydroxide ion. So now we have two reactions, the acid in water and the base in water. We're going to use Hess's law to combine these two reactions to see what we are left with. And you'll notice the HA cancels out, reactants and products. The A- cancels out in reactants and products. And we are left with the reaction for the autoionization of water. All right. Now recall for Hess's law and equilibrium constants, if you know Ka and you know Kb, or you know any K values, when you add two reactions together, 1 and 2, you multiply their Ka, or their K constants, or equilibrium constants. So here we find Ka times Kb equals K for this new reaction, which happens to be the autoionization of water, which is Kw. We now have a new equation we can use. Ka times Kb equals Kw. So let's put that equation into practice. Here we have benzoic acid. There's the hydrogen ion that comes off, and we're given its Ka value, 6.46 times 10 to the negative fifth. Find Kb for the benzoate ion, which is the conjugate base of benzoic acid. All right, go ahead and solve.